All right, guys, you ready? I started the recording. Did my one job that Guillaume gave me today. Okay, so Kurt just talked to you about empirical models to estimate IOPs from reflectance. And this is part 2, where we're going to look at semi-analytic models. And it's actually the basis for what we're going to do in lab this afternoon. So I do want to return to this figure here. You've seen this, or this paper, Ken showed this last week, Kurt talked about it today, but it's just, sometimes it's like the smallest amount of data can be, if you're thinking about it correctly, can just really change the field. And so I just want to go through it one more time so that you don't dismiss some of the older papers from which you've learned everything. And what we're doing now is in decimal points, right? So the big thinking. So this is the original set of measurements of reflected light, percent of incident light, measured on an aircraft over the ocean. And they were at one station, I can't remember where it was, I think it was Gulf of Maine. Also, it's great because that. They're at the Gulf of Maine, and then they were a series of altitudes from 600 feet up to 10,000 feet. So basically, they brought the aircraft and just kept flying over the same spot and measuring the amount of incident light that was reflected as a function of gradient. Okay? So it's obvious that the closer you are to the ocean, the darker it is. The higher you get, the brighter it is. Why? The atmosphere. The atmosphere is scattering light up into the sensor that is on an aircraft that is getting increasingly high. Okay, so that's what is responsible for that. Then they went to the same altitude and flew over a transect, starting at Georgian Shoals and going on to Sargasso Sea. And because they're at a low altitude, you can see that percentage now, this is like way over 10%. We're now looking down at these 2% ranges. And what you see is that there's, as you get from offshore to onshore, the reflectance goes down, right? Due to what? Absorption and so it's less scattered, right? Because if it was more scattered, it would get brighter. But instead, the ocean is getting darker because of absorption, right? And in particular, absorption by phytoplankton, which known back then as chlorophyll. Phytoplankton were really just thought of as chlorophyll molecules floating in the ocean. Right? We know that that's not true, they did too, but we also, it was just easier to talk about everything as the scalar chlorophyll rather than absorption spectrum. Okay, great. All right, so we're going to talk about inverse reflectance models, but just to remind you what a forward reflectance model is, you start with the infinite radiance, you propagate it through a medium using the IOPs for that medium, and then you can use the radiant transfer equation to do this, and you did hydrolite last week and presented great data this morning. We're also going to do Monte Carlo, and that's going to be week 4 in the current schedule. So you start with radiance and you end up with the AOP. Okay. In this approach, we're going to be inversion. So in this case, we can't run the radiant transfer equation in reverse. The antihydrolite, although for 2 more years. So we have to make approximations for the radiant transfer equation. And those can be done sort of by using some empirical models, which basically are not really much of an approximation, although we can show you some, or these semi-analytic models. And depending upon models that you're looking at, some are more semi-analytic and some are more semi-empirical, depending upon how they parameterize the reflectance in terms of IOPs. So you start with the AOP, such as reflectance, and you derive the IOPs using this inverse model or approximation for the transfer equation. Okay. So the IOPCG, the International Ocean Color Coordinating Group, has been publishing a series of reports. How many people have looked at any of these reports? Excellent. How many of you looked at more than one? You should look at more than one. There's some really, really great work published in these. And even though some of them are old, they're still pretty illuminating. So this was one that came out in 2006. It was headed by John Pingley. And it was looking at testing algorithms, comparing algorithms on synthetic data sets and some real data sets, and sort of the applications of these models. So I just wanted to show you some thoughts on chapter 1, which is kind of an introduction to this report. And it was written by Ron Zannefeld, Andrew Barnard, and John Pingley. And it asked the question, why are inherent optical properties needed in ocean quality remote sensing? Because we can put in a radiance distribution and we can get chlorophyll concentration, and we can also get a production rate, and we can also get particle concentration. Like why do we need these IOPs when we can already get all of these data products from some empirical based model, be it a band ratio or a neural network? And so here's the example for the OC4 algorithm. And so we can estimate chlorophyll. We see that chlorophyll is related to this ratio. We don't really care why. Now, hopefully after 2 weeks of this class, we know why the reflectance ratio changes in function of chlorophyll, but we don't know. But we don't know like what's actually leading to some of the variability in here. It doesn't matter, you fit a curve. Right? And I will tell you that the bending of this curve down here is anything but driven by this data set. You actually have to get put a data point down here for pure water in order to make that curve fit. And my student discovered that one. I'm trying to reconstruct from this data set, reconstruct this line, and couldn't do it. Something called NASA. Have a tie point down here to drag this curve down. That didn't show up in the publication.
Why would it, I mean, much like it would fit decreasing exponential better?
It's this scale. Well, there is actually a change in slope in these lower level scales. So chlorophyll isn't what's impacting radiance, as we know, it's inherent optical properties. And so really, in order to reconstruct the radiance distribution, we need to know those properties, and those properties are determined by the properties of the constituents in the water, and we spent 2 weeks learning about that. And so if that's true, that they're determined from these constituents, then what we can say is if we invert the radiance to get the IOPs tell us something about the components, particulates dissolved in water. And those particulates, we can then start to say, well, what are organic and what are inorganic? What's living, what's phytoplankton, what's bacteria, the phytoplankton, what is chlorophyll, what's accepted. So that original black box, which related radiance, or radiance reflectance to chlorophyll, went through all of this step to get to chlorophyll. But look at all of the other information that's available that is leading to some of that variability. And so that's where these non-black box approaches, where they become useful. If you want more than just chlorophyll, and you want to understand why the chlorophyll model made it work. Okay. So there are also some philosophical things to think about when you're deciding whether to use the empirical model or the analytic model. So the empirical model needs to be regressive models, machine learning, neural network. The thing that I ask myself is, do you need an answer? Are you a manager and you need to know whether the turbidity in the water has increased and that would indicate that you have Ebola? Or you need to know whether the chlorophyll is beyond the threshold level, because that means you have a food. If you need an answer and you need it fast, like that is exactly what empirical models are great for. They give you the answer, and it's based on history. Do you need to forecast based upon your historical knowledge? That is also a great place to use empirical models. And you don't have to know why they work, you have to know what they do, and particularly know networks they do. The analytic model, or mechanistic, sometimes called theoretical models, it's like, do you want to know how it works? You want to know why something is happening. And do you want to be able to resolve change in the ocean that's different from what you have observed in the past? That's when these approaches start to become useful. And really, when you think about it, you have both. So kind of employing both kinds of models together I think becomes incredibly powerful. All right. So Jeremy and colleagues published a really nice summary of where we are in terms of retrieving IOPs from reflectance. And so I'm going to take a couple of figures out of this publication, but it's really worth reading. Great job. Okay, so this is a figure from that paper. And they go through all of the different types of models and sort of strengths and weaknesses of them and give examples. And so the first thing to think about is, where are you measuring reflection, right? You could be measuring it at the top of the satellite. I'm sorry, at the top of the atmosphere out of the satellite. And so you'd be measuring the normalized water leaving radiance, right? Top of the atmosphere. And Kurt talked about that last week. You could be making your measurements above the surface. And so that's the remote sensing reflectance, which is the ratio of water leaving radiance to downward AP radiance. And you guys did this. Where did you do this in the home last week? On the dock. With me? I think of the manual. When you were standing on the dock and you were pointing a radiance sensor from air to measure the amount of light radiance emanating out of the surface into the solid. That's water leaving radiance, right? Or you can do below the surface, and below the surface, and you notice we have different symbols here. It is far from standard, but we're trying to push it based upon this paper, the NASA, trying to push NASA's terminology. So it can either be E-radiance reflectance, which is the ratio of upwelled E-radiance to downwelled E-radiance, or upwelled radiance to downwelled E-radiance. So E-radiance reflectance, radiance reflectance, and where did you do these? So COPS was reflectance. Where else? And the buoy, right? So both of them are measuring the upwelling light just in. Okay, excellent. And they're related to each other, as you showed. Okay, so in deriving the IOP from Inversion, there's a series of stepwise that you can think about, and all have great utility. So the first thing you can do is you could just measure your total IOPs, right? Just measure IOPs, because you can derive the constituent ones, right? So you can get your absorption and backscattering corrected for water, and you can break it into components of phytoplankton, non-algal particles, CDOM, etc. That's an inversion model. So how would you do that? Where would you start with that? With an ACS and DB3, or hopefully hyperspectral DB. Yeah, right? So you can do that, and there are models that you can partition the total optical properties into their components. Okay, so that's just steps 3 and 4. You stay in the water, you stay with the instrument. Okay. Or you can measure the remote sensing reflectance, the radiance reflectance, and you can either derive first the total IOPs and then break them into components, or there are models that take you right from reflectance immediately to the component IOPs and think of phytoplankton. So right from reflectance to phytoplankton, rather than going through a step of estimating absorption and then decomposing. There are plenty of models that do one or the other, right? And then the next step would be the top of the atmosphere radiance. And these are all 4 of these steps. And you can go stepwise from top of the atmosphere to the surface, to total IOP, then to components. You can skip the RRS, computation of RRS, and go right through the total IOPs and decompose them. Or there are a couple models out there that start with top of the atmosphere radiance and go immediately into component IOPs. And so each one of these will have different sensitivities. All right, so let's consider the ocean that's comprised solely of water in its real form and some absorbing material, say CDOM ocean. How is RRS going to change as we add CDOM absorption? It's going to decrease in the blue. Maybe in the green a little bit. What about the red? It'll be the same, right? Because we're not adding that. So it's just going to get darker and green, right? All right, now let's look at water and a scattering material, like maybe a concrete core balloon or suspended sediment. How is it going to depend on that scattering property associated with that? Yeah, it's just going to get brighter all over. If it's a white scatter, the whole thing is going to get brighter. And so as you think about reflectance, absorption makes it darker and can change the color, and backscattering makes it brighter and can slightly change the color. Okay, so that's what gives us heuristically this intuition that reflectance is going to change as we back over A. And how many people have knew that before they came, that reflectance is proportional to be back over A? Well, now all of you should know that, right? One of the most common equations that we use. R is equal to something times B back over A. Okay, so I want to just give a little bit of history about some of the approximations and semi-analytical inversion. So we start with a Howard Gordon ocean, which is defined as the water being homogeneous. Plane parallel geometry, only the sun is coming in at a certain angle, the surface is level. The sun is a point in a black sky, there's no skylight, and there's no internal sources, so no reflective, or no fluorescence, no water, Raman. All right, so let's solve the radiative transfer equation for reflectance. Remember this from the first day? Does it feel more comfortable now? Now that you know what L is, and theta and phi, and now you know what absorption and scattering and theta, scattering from one angle to another angle. All right, so one approximation is something called the successive order scattering, which is where you take this equation and you separate the radiance into, for each depth, into radiance that hasn't been scattered. And radiance that has been scattered once, scattered twice, scattered n times, right? So you have n number of equations. Then you can use the next approximation, which is the single scattering approximation, which says that we're only going to consider the light that is unscattered or scattered once. So we're just going to take the first two terms. Okay. Then we're going to do something called quasi-single scattering, which is the next step of this, which says, well, if you look at the volume scattering function, it's really, really peaked in the forward direction, right? 4 orders of magnitude, when it comes down, we do some back scattering here, but we have most of the scattering is in the forward direction. So if light's coming into the ocean, most of it is scattered downward. So if it's not, if we're in the L1, the unscattered radius, we never see that again, right? Because it's just not scattered. And if it's scattered once, we also don't see it if it's forward scattered. It's just heading down. It is not part of the radiant field that's going to make a back up opposite. And so in making this approximation, what it says is that forward scattered light is the distance unscattered. So we are going to replace in our equation, we're going to replace scattering with back scattering, because forward scattering is like unscattered.
So when you use forward scattering, you get over approximation.
Well, if you add it in, well, so what you're missing is multiply scattered forward light. So the first step is you're missing multiple scattered light. That's this one. And then the second is you're missing multiple scattered forward light. Okay. So that means that scattering, which is forward plus back scattering, gets replaced by what? Heating, right? That means that attenuation in the radiative transfer equation is replaced by what? What? Who said it? A plus BB, exactly. And the single scattering albedo, which is the back scatter or the total scattering over the beam attenuation, is replaced by BB over A plus BB. So now you put that into the solution of the radiative transpose it. And Kurt has done a beautiful job on the web book and in the PDF. Where he actually goes through the entirety of that solution of the scattering approximation. It's really elegant and beautiful. And you solve for the upward and downward radiant fields. And lo and behold, what you get is that the reflectance is proportional to backscattering of backscattering. That is how you get to that equation that everybody uses, right? They don't talk about it. They start with, all right, the feedback over A equals feedback, right? Well, that's how you do it. There's a lot of work that went into that. And just the thing that's really important is that it really only holds reliably for the surface. So people who start using R equals feedback over A equals feedback at depth, they didn't read the original paper. So you have to be really careful making that approximation once you're away from this.
How deep is the surface?
You have simulated data from Hydrolake, and you can go and figure it out yourself. Right? And I would encourage you to do that. And it will depend on what you can simulate, right? So do a bunch of different runs and figure out, like, is it the top opposite of that? Is it 5 meters? Right? How do you want to be thinking? You want to be thinking about this in terms of meters or opposite depth? And how many opposite depths? And I do encourage you to do that. It's very
Essentially, if you plotted R and you be able to do the same plot, you can see a difference.
yes, very good. Yes. Excellent. Okay, so if we start with the remote sensing reflectance, or maybe the radiance, in this case, the radiance reflectance, what you find is that you can express this ratio of radiometric measurements as some series of the B back over A plus B back. And Howard found that 2 terms, so you have the first term and then that term squared. And, you know, by fitting some components, you can get an estimate of what these scalars are in front of that. Generally, people ignore the second term because it's relatively negligible, but this is what it would look like, that second term. And in the E-radiance reflectance, Morel found that a good coefficient is 0.33, sometimes it's 0.31, but 0.33 times V back over A is the most simple term for E-radiance reflectance, and one that was used historically. Okay, so questions to there? Yeah. Yeah. Little r is LU over ED. Big R is E over ED. So the difference is going to be the difference in the solid angle collection of the radiant tensor compared to the radiance. And so if you look at this first term, it's about 0.09, and this is 0.33. So that tells you it's about a factor of 5, right? That's LW, which is already taking things through the interface. Yeah, exactly. And no matter what paper you read, they will express it differently. But in your mind, just develop a, you know, these are the terms I'm going to use and just write it in. You should read papers, yeah.
Genes can be more widely.
Because some people don't ignore it. So it would look, if it's generally ignored, then this whole term goes out and you only let I equal 1, which would be 0.0949 times B back over A plus B back. You could add the next term, which is plus 0.0794 times B back over A plus B back squared, right? So it's a series. And you just start lopping things off as they become negligible or you can't resolve them within your measurements. All right. So again, what's going to happen to R as I add CDOM? Darker and greener. Okay. What's going to happen if I add heterotypic bacteria? Yeah, they don't have pigments. They might have a little non-alpha particle absorption, but it will be small relative to their scattering. So it'll get brighter. Don't want to swim in that water. Increases phytoplankton? So it could be darker and greener, right? And sort of, it could be, well, it didn't really show up on my screen, this is much darker. This is lighter. It depends on their absorption backscattering, right? So it can be brighter, but it will certainly be greener. Okay, good. So I want to look at an early solution to that forward problem, and that was the basis for all of the semi-analytic inversions that you will see since then. So, estimating chlorophyll from the reflectance ratio is what Kurt just talked about, but in 77, Morel and Pierre were already investigating the IOP part of the problem. So back to Ron Zanofeld's first chapter in the IOCCG book, Why Do We Need to Know IOPs? They were already nailing it back in 77. How many people have read this paper? An analysis of variation in motion color. Please read it. I know it's old, and I know that it's got like bad graphics. I will show you the bad graphics, but every time I read this paper, I learn something new, and I've read it a lot of times. There's so many nuggets of information. And what's most humbling is to realize how much they understood about how light in the ocean works, and how much they did with like no measurements. So they didn't have measurements of basically anything but irradiance reflected, and yet they were able to basically do a serviceable semi-analytic inversion. And now we are having embarrassment of riches in measurements, and we need to move forward with better thinking, but we have so much data, it's overwhelming. So it's like these opposite problems. So read this paper, it will inspire you and do great things. Okay, and read it more than once. All right, so here's what they had. They had E-radiance reflectance, but they didn't have radiance sensors back then. And these are the spectra, lambda, and reflectance, EU over EV. And it's on a log scale, but you can see there's all the different shapes you all have been seeing over and over again. And then they used the quasi-single scattering approximation and said, all right, well, we're going to relate it to B back over A. They read Howard Gould's paper. So the goals of the paper were to try to explain all of these variations using the IOPs rather than just saying chlorophyll, right? And to model those IOPs in order to do a forward model to predict R. And then that became the basis for semi-analytic inversion. Okay, so the first thing they had to do was parameterize backscattering. They didn't even have backscattering really at one wavelength at all, right? So they said, okay, well, this is simple. We know that scattering is scattering by water and scattering by particles. And we know that backscattering is backscattering by water and backscattering by particles. And we know, because Andre Morel measured it, that the backscattering is proportional to lambda to the minus 4.3. And, or did he measure it, or did he derived it? Now I'm blanking. And that we know that if we just have particles in the water, theoretically from mean theory, they've got to have some sort of dependence on wavelength. All right, so they said, okay, well, if we know those things to be true, then we should be able to come up with an expression for backscattering as a function of water. Right? So they have this graph. So what is this axis telling you? The particle backscattering, right? So total backscattering. So when it's 1, what does that mean? There's no particles. But you can assume the ocean's backscattering is determined solely by water, which we know, right? And what happens if it goes to 0? There's no water, but there is water. So what does that mean? There are so many particles in the water that the backscattering properties are determined solely by the backscattering properties of the particle, which we're going to use a power function for. Okay, what's this axis? Yeah, they're looking at the ratio of the backscattering in the blue to the backscattering in the red. it's a slope parameter, right? They don't have an exponential slope, so they put the ratio. What's the ratio, right? So when it's 1, that means it's flat, right? When it's 14, it means it's really steep. So they're going to come up with a relationship between these two things. All right. So that's a proxy for spectral slope, and that's the fraction of BB that can be accounted for by water. All right. So this is what they come up with. And what it says is that when water dominates over here, at this point here, the spectral slope of water, which we know is 4.3, leads to this 380 to 700 ratio of 14. 14 magic? No. If they just put 2 on the and as you increase the particles, which means you're moving this way, the value, the spectral slope is reduced, and it's reduced down to that value for pure particles. But it's dependent upon this NP. And NP is the coefficient on the power, on the wavelength. And so don't confuse that with index of refraction of particles. It is literally the coefficient that determines the slope of the power law. Okay. So think of it as eta, which is what we use now, not. Okay. So this is when particles are spectrally flat in terms of the backscattering, and this is when they have a -1 dependent. And so you can see that these lines are somewhat different. Okay. Pretty clever. So they said, okay, well, let's try this out. So they went to some blue waters. And said, okay, in blue waters, we're going to ignore everything but just some particles. Blue waters don't have phytoplankton, that's why they're blue. So maybe we have stuff in the water, but not much, and it's particular in nature. It's a model. Just looking at it, it's a model, right? We can say whatever we want. We're under Morel and Louis Freire. Okay, so that says that backscattering varies, but it's going to vary according to that, 0 or -1. Okay, so here is the reflectance, EU over EB, and these are models. So they're all high in the blue, not surprising. They're all low in the red, also not surprising. It's a log scale. And the difference between the dotted and the solid line just depends on the slope of the particle backscattering, which the slope varies due to what?
Size.
Yes, particle size. So they were allowing particle size to vary. And you can see that on a log scale, it varies a little bit, which means it varies more than a little. Right. Then they went out to Crater Lake, which they thought was going to be like some of the purest blue water. And they took some measurements, and those measurements are in black. Those are the measured spectra. And then the dotted lines are some of the modeled spectra from over here. And what they found is that they could do a really good job of modeling the reflectance of a pure blue lake. How many people have been to Crater Lake? Oh, so beautiful. Go to Crater Lake. It's so blue. And so you can do a really good job of modeling the reflectance of this clear blue lake, and also the Sargasso Sea, which is a pure blue ocean, just using water and particle backscattering and a power law. Wow, that was actually a huge accomplishment. That was just, something they just tried to do, and it worked incredibly well. So then they said, okay, well, it's easy because we know what water is. Let's start moving into green waters. We're going to have 2 cases. Case 1 and case 2. Sound familiar? This is where case 1 and case 2 originally came from. They didn't just find it as here's our case 1, here's our case 2. It's we've got these 2 situations. Okay. In our first scenario, it could have been called scenario 1 waters, right? I mean, literally, it's just so funny to me that this is where it happened. Now people are like, case 1 and case 2. Okay, so in case 1, quote, chlorophyll concentration is high relative to the scattering coefficient. They give a really nice description in these waters of how the reflectance changes as you increase chlorophyll. And they talk all about the different parts of the spectrum, brightening and darkening. And for them, it's based upon phytoplankton. And they describe this as a Vtype.
And I'll show you what that means, and I want you to think about the results you showed this morning. Case 2 is, hey, in our other scenario, relatively higher inorganic particles than phytoplankton. Relatively higher. I don't know, factor 2, I don't know how much higher, it's just relatively higher. People hang their entire careers on case 1 and case 2 algorithms. I'm serious. That's ridiculous. Like, I don't know, more particles. When it doesn't work, it's probably case 2. Okay, so they have this really nice description. Sorry. They have this really nice description of how R changes as you increase turbidity. And when you increase turbidity, you also have to think about CDOM and non-algal particles in your IOP. So there's absorption in there too. It's not just backscattering. And they call these the Utype. Okay, so here's an example of the Vtype. And these are the ones where phytoplankton are dominating scattering. So now they said, okay, we took our pure water model and we're adding phytoplankton. And because phytoplankton is dominating, we're going to allow backscattering to be proportional to chlorophyll. Right? Does that sound familiar? Have you guys heard that before? Yes. Oh, Beer's law. No, not Beer's law. Hydrolyte, right? Those are the case 1 algorithms where everything's proportional to chlorophyll. So here are their measured spectra. Again, you can see it's on a log plot, but you see this really nice change in the shape of the reflectance curve. The top one is for low chlorophyll. The bottom one is for high chlorophyll, very high chlorophyll. And what's interesting, of course, is that you see that it gets darker in the blue and it becomes more green. What's really interesting is it doesn't change that much up here, right? So really what phytoplankton are doing is not so much action in the red, in the green and the red, but a lot of action in the blue. That is the basis of the band algorithms. This doesn't change, so you're just looking at this blue to green ratio of a function. All right, the second type is the Utype, or sediment dominated. And they said, all right, in addition to our water model, and then we're adding phytoplankton, we're going to add some other particles that absorb, and that'll be CDOM and non-algal particles. They called it P, but that's okay. We just allow CDOM to be put in there. And we're going to see that the phytoplankton absorption is proportional to chlorophyll concentration, but that the particles and their absorption and the backscattering are not proportional to chlorophyll in this case. Okay? And so what you see here is that as you increase the particles, it gets brighter. So how familiar is this to you based upon what you did with hydrolyte? What do you guys see?
Sarah looked at the different mineral compositions.
Look familiar? Yeah, and it's basically increasing the reflectance all the way across the spectrum. It just gets brighter everywhere. It gets whiter, right? And that's that Utype. And so when you think about this, what were you doing when you found these types of spectra, these V-type spectra? You saw that too.
All the minimums.
Mm-hmm. Didn't you see some spectra that looked like this V-type?
Yes, because they were lower.
Lower mineral concentration, and there was a lot of absorption happening in the blue, increasing absorption. So the question is, when you have low but highly absorbing minerals, or you have CDOM, it can be difficult to separate them in these types of flowers. Okay. So they also saw some increasing in CDOM. All right. So they came up with this generalized semi-analytic model. They said, all right, absorption is going to be equal to water plus some phytoplankton absorption. And we don't know much. We've measured it in the spectrophotometer that was sort of made, not for this, but they made it work for filter paths. They were great. And they said, phaophytin shows up in there too as a pigment. So we're going to actually add the chlorophyll and phaophytin because it gives us a better result. We're going to multiply it by some phytoplankton spectrum that's been normalized to chlorophyll. And then we're going to take the magnitude of scattering and say, well, some fraction of that is going to be driving our particular absorption, and it's kind of exponential. And then we're going to have backscattering, and it's water, and it's the particle scattering, B minus BW is BP, right? And they actually could measure B. way, times some backscattering ratio, right, for particles. Now, they knew water scattering, and they knew water backscattering, and they measured V at 1 wavelength. Okay. And so they assumed that the backscattering ratio was spectrally flat, and they adjusted the particle scattering to match the reflectance. They just were scaling everything to 500 just because they didn't have backscattering. They didn't know what that ratio was. So here you have it. The observed spectra from, that spaghetti plot of spectra from first figure are in solid, and the model using this model and 0.33 times V back over A gives you this fit, which is really stunning, right? It isn't a log, but they're able to reproduce the V-type, the Utype, and over a range of chlorophyll concentrations from 0.2 to 6. And it was really astounding that at that time, with that little technology, they were able to do that type of modeling. So then they could say, okay, well, great, now we can go and estimate chlorophyll. And at that point in the paper, you're like, no, you just estimated the IOPs. Why are you going to chlorophyll? But back then, chlorophyll was what the product that everybody wanted from satellite. So they said, okay, we're going to take the blue to green ratio, plot it as a function of chlorophyll and phaophytin, and we see this linear relationship, and so we can estimate chlorophyll from space. And in fact, yay, chlorophyll from space. So that same line turns out to be this log ratio. You can do it for other blue-green ratios, depending upon your sensor, your sensitivity. Yay. And then those of you in the audience might say, wait, there's an order of magnitude difference for each reflectance ratio. I can give you an order of magnitude difference in chlorophyll concentration. Okay. And it's because there's these variations in ocean color are not just driven by pigment, they're driven by the IOP. And so that was the point when it was sort of like, okay, this is why we need to move further and move beyond chlorophyll, and why you're all sitting in the audience today. So, okay, questions on that? Feel comfortable? Read the paper, learn something new. All right, if the water's green, OC4 is going to give you a chlorophyll value. Is it always right?
Yeah.
Where would you be suspicious? A green dye kind of just throwing blue absorbing material in the water. There are things that just throw blue absorbing material into the water. Like what?
Rivers.
Rivers, thank you. Rivers, Pi and CUM, are basically green dye. And by plants, I mean vegetation. The breakdown of vegetation is a dye plant. It's Brad. Okay. And so this is demonstrated really nicely by that neural network that Kurt showed you, that the algorithms were really good at identifying green water that wasn't chlorophyll in the rivers on the coast of the Gulf of Maine. And if you look at the seasonality of those, you see that they don't look anything like phytoplankton seasonality. It's river discharge, right? So, excellent. Okay, so now we're going to do the inversions. All right. So in the 90s, which feels like forever ago, and it was, there were a lot of papers that came out. It was like, Merrill here wrote this in the 70s. And then, like 2 years. All of us. Everyone is reading the paper, but not getting it. And then suddenly it was like, wait a minute. Hold the phone. We can get IOPs from reflectance. And literally, within like 3 years, 5 papers came out, all independent, all basically doing the exact same thing. And it was just crazy. I don't know why this happens, but it does. So here's how it works. It turns out that if you start with this equation, that reflectance is proportional to backscattering and absorption is backscattering, and the F over Q is in there, depending upon where you're measuring reflectance and with what. It turns out that, duh, all of the IOPs are additive, so we can separate them into their components, like phytoplankton, CDOM, NAP, or particles. We can now measure them with a spectrophotometer and plot them, which they didn't have really that capability. We can model what the particles might look like, what small particles might look like, large particles, spectra. And so if you can do that and you say that these are additive, the other thing that you can also say is because of Beer's law, each one of those can be expressed as a shape and some magnitude because absorption, sorry, he's just running away from the sprinkler over there. Absorption is proportional to the concentration of material that's being absorbed, right? So we could say, well, instead of just having a phytoplankton spectrum, we could come up with a characteristic shape of phytoplankton, scale it to something like chlorophyll again. But it would allow us to have one part that defines the spectrum in a non-dimensional way and one part that defines the concentration of that spectrum or how much absorption, right? So for phytoplankton, the natural normalization would be chlorophyll concentration. So we say that the component is the concentration times the specific spectrum, which is the scalar times the vector, a magnitude times the spectral shape, however you want to call it, or an eigenvalue times an eigenvector if you're using linear algebra terms. Okay. So you can now go from your components to expressing them as this this product of a concentration or magnitude times this specific absorption or backscattering spectrum. Or you could break them into further constituents, right? We don't just have one kind of phytoplankton out there. You might have many different types of phytoplankton. So you could have one for diatoms, one for diaplasmids, one for green alga. You could have as many different classes of phytoplankton in here if they had a different shape absorption spectrum. Do they? Did you measure them? What were the names of the phytoplankton absorption? The phytoplankton measured absorption on Denaliella, Sorry, excellent. So that's just two, and they were really different in spectral shape, right? Now you could imagine you could break it into individual pigments. You could have a spectrum for chlorophyll A, spectrum for chlorophyll B, one for pyridinin, one for fucoxanthin, one for diester ether, oh, what's the name the Karina has? Anyway, I can't remember. Very specific pigment. But you could break your absorption instead of into classes, you could break it into pigments. What Ali Chase did. CDOM, if you are an expert chemist and you know that the absorption spectrum or the specific absorption spectrum for carbon perhaps changes for your various compounds depending on their aromaticity, you could put in multiple CDOMs which would have different spectral slopes. And by inversion, you can get out estimates of each of those different components. Okay. And the same thing for non-alpha particles. If you want to separate it into minerals and living bacteria, living zooplankton, tidal particles, you could do that. It becomes incredibly powerful. And you can do the same thing with backscattering. You could have backscattering by different types of particulate matter, backscattering by different sizes of particles. So this becomes incredibly powerful as long as you have enough wavelengths to be able to resolve all these unknowns. All right, so we put it all together. I just did it in terms of components, and you see that it's very complicated. So the waters are known, absorption by water and by backscattering by water. The eigenvectors are the spectra associated with each component, and we say that we know them. We can measure phytoplankton absorption. We can normalize it to chlorophyll, we can use that. We have an analytic function for CDOM absorption, which looks like what? What's the shape? Exponential. You can just have an exponential function that then you can allow the magnitude to vary. So these are known because we're putting these into the model. And then we have the eigenvalues, which are scalars, which tell us how much of each one of those eigenvectors we're going to use. Okay? And that's what you are estimating. So in the hyperspectral world, like if you had multiple wavelengths, you could have multiple constituents per component. So your phytoplankton could be all of your phytoplankton. Your NAP could be various NAP constituents, CDUM, various CDUM constituents, backscattering various ones. And they show up differently and make this just a little bit more complicated equation, but whatever. Okay. So the next step is that we have these input vectors, and then we just perform a regression against a measured reflectance vector. You put in your measured, you put in your eigenvectors, and you estimate the values of the eigenvectors, estimate the eigenvalues. And so what that's telling us is how much of each absorbing and backscattering component we need to reconstruct our measured spectrum. So if you think graphically, this is what it looks like graphically. I have reflectance and I have backscattering by two components, that's in the numerator. And I have absorption by my components, that's in the denominator. And you're literally adjusting them in order to match this spectrum. Okay. And so I would look at this one and I'd say, well, there's a big dip here at 440. So I have to have something that is reducing the light at 440. Well, that means I'm going to have some phytoplankton. So you can kind of like, look at this and figure out what you likely have. Notice that I don't have the BB over here because there wasn't enough space. Your BB would be on the bottom as well. Okay. All right. So the papers that came out, the flurry of papers, really the only difference between them is how they define their eigenvectors that went into the model. And here's an example of the absorption eigenvectors. So this is one that I did based upon phytoplankton, a bunch of curves that I measured and just took an average. Zhangping Li characterized spectral shapes based upon if it's a unpackaged versus packaged. It's an analytic function, so it doesn't have any of the side peaks. There's no picking in there. And then the original Garver and Siegel had this dotted one, which was based on optimization of their, well, I'll talk about optimization, but those are their phytoplankton curves. So if you put them all together, you can see they're really different in terms of what the chlorophyll specific absorption is. So it's always good to plot out their data so you get a sense of what it looks like in terms of what you're used to, right? And what seems to make sense to you in the ocean. Then there's their inversion method. And literally in one of the papers, it was estimated by I. And as Emmanuel said, people do stuff in Excel. And this particular person wrote a program and literally just modified in Excel to get an estimate. Okay. We're going to do that today, actually. It's a lot of fun. That's not how I did it, but that's okay. You can actually linearize this equation, and I've given you some slides in a different document that show you how to linearize this and turn it into a linear regression. You can do a nonlinear least squares, and you can even optimize nonlinear least squares. Basically, they're all just minimizing the difference between measured and modeled. And then there's the differences in the papers between how they validate, or if they validate, and if they did a narrow analysis. Did they validate it with independent data? Was it tested over a broad range or a narrow range? But that's something you should always look at when you're evaluating new models. So I'm not going through all of them, but I've given you a PDF which goes through each one of these models and talks about its strengths and weaknesses. And so the PDF is available for you to kind of go through and look at them and things to notice when you're reading them. Yeah, so that. What's our time?
11:23.
Okay.
So would it be correct to say like all of these are basically resolving?
Yes. So you start with this, and what is the measurement that goes into this approach? Yeah, you have to start with the measurement of reflection, right? That's what you give the model. That's the only thing you give the model. So you go out and you make a measurement. We measure the radiometric properties and you derive it, an AOP, okay? And then what data do you need? How would you validate it? In situ A and B back, right? So you are starting with a measurement of this, you are estimating proportions of this, and then you need to validate against that, okay? So here's how that works. All right, so I'm going to show you mine because I'm most familiar with it, and I can tell you all the weaknesses of it, and then I'll have to tell you all the weaknesses of other people's. So I started with backscattering by water, and then I allowed for particles to come in 2 different flavors. Surprisingly, the ones that were on period 2. And the thinking was particles are either large, in which case they're expected flat backscattering, or they tend to be small as you head out into the open ocean, and you're going to have a more spectrally varied backscattering spectrum, right? And if you're somewhere in between, your regression is going to say, well, I have a little bit of this and a little bit of this, and if you add it together, you can get a spectrum of infinite different slope in between there, right? So I don't have to say a priori what that spectrum that reflectance is. I let the regression for me. So, so those are my 2 basic vectors for backscattering. And then I have this absorption. So I have water absorption, phytoplankton from the data that I collected in another paper. It was just a bunch of mostly coastal phytoplankton that I averaged, but you know, they've got nice peaks that are associated with pigments that we can identify. And because I don't know why, but at the time it seemed prudent to combine CDOM and NAP into a non-phytoplankton that consisted of dissolved and particulate. And I found after I did a bunch of data analysis and reviewed other papers that if you combine them together, you tend to get a slope of 0.0145. I was going to do it again, and of course would separate them, but I didn't. Then I had all of my measured spectra, and Kurt showed this before. I went on 4 cruises. Well, I went on a lot of estuary cruises in Puget Sound, but I went on the Gulf of Maine, Oregon coast. I went on a bunch of cruises. I collected a bunch of data. I had a gradient sensor that I could flip so that I could get ED over O, I should say EU over ED, sorry, that should be E. And I went to a variety of optical regimes with really high rates of chlorophyll, phytoplankton absorption, and the backscattering coefficient. And these were just the sort of examples of 4, one from each region. But they're really different spectral shapes. You're going to get these data sets today. So you run the model. You pick your spectrum from your LUED or EUED, and then you put in the basis vectors, which are like these, whatever, absorption and scatter, backscattering basis vectors. And then I used a nonlinear least squares minimization to estimate the eigenvalues. And then you take those eigenvalues, you multiply them by your eigenvectors, and put them back in the equation, b back over a plus b back. And you get a reflectance. You get a modeled reflectance. You compare that to your measured one to make sure that the minimization looks good, right? So it looks like this. These are the 4 examples. The measured are always in color, and you can tell they're measured why. Then the model. Arguable, yeah, maybe. What else? There's fluorescence, right? The model doesn't have fluorescence in it, which was intentional, and I'll show you why. But that's how you can always tell.
What is the there's no fluorescence?
It is fluorescent. So, that's what I'm going to tell you. Oh, yeah. That's why I didn't put it in there, because I discovered this, and I was like, oh, that's interesting. So, what do you walk away with when you just see this? This is one model. Nothing changes. The exact same eigenvectors. All I did was vary the magnitude of them. That's what I thought too. It's a 6-component model. Water absorption, backscattering are constant. And the only thing I'm varying is the amount of small particle and large particle scattering, the amount of phytoplankton of an average generic spectrum, and combine CDOM and NEP. That's it. spectrum. Just by varying the relative concentrations of them in a least squares way, you can reconstruct from 9% reflectance down to like 1.5% reflectance. Maximum in the blue, maximum in the green and yellow. So just those components explain most of the variability in the global ocean. Anything else is gravy, right? What isn't explained can be exploited. So where it doesn't match, it means that your basic spectrum is not a good representative of your environment. So for example, this is Daybob Bay. It's a really interesting place in North Puget Sound. So the difference between the model and the measured here looks like what? It's something like that difference decreases exponentially from blue to red. CDOM. It was not a good model for CDOM. CDOM's slope there was much steeper. CDOM dominated the non-algal particles, and so the model underestimated. So, and here, you know, this looks like a pigment band right there. There's definitely a little pigment band there. You start to see these little places where it's over or underestimated. And if you look at the difference in reflectance in those places, they show up exactly where pigment peak shows up. Either you had too much pigment in your basic spectrum or not enough. And that becomes incredibly powerful for the second level of analysis, right? Does that make sense? Okay. All right. I'm going to talk about the results after we get tested. I just have a couple more slides, but I think probably ready to go. Any questions on this so far?
So there, like if you pull this model for your components, you just pull from a library, or was that like from averages?
So when I took this class, I was looking at Absorption, but teaching Absorption, and I measured a ton. And then I went to work with Mary Jane, and I was sure 1,000 from everywhere I went. And I just averaged them. I mean, there's nothing magic. It is really generic. I'm giving it to you. It's reasonable approximation of an average spectrum size for crystal light, right? But even that, this is a subtropical gyre, right? Even that does pretty good job. I would obviously, if you had different spectra, it's better to do it, and there's definitely ways to do it better. But it's surprising that just generic spectra can be convolved into this much variability. Which says that now that you can do better on basic vectors, you can do so much better. You can exploit all of these little differences here with different phytoplankton absorption options. So,
Coastal data, did you define coastal as coastal
my
estuaries?
gosh, yeah. So, I mean, you know, I was 24. I had this much oceanography. So I defined coastal because I did a coastal transect. It started at the coast and went into the gyre. And then I was like, ooh, it got really different. So I'm going to have an arbitrary boundary where I'm suddenly call it oceanic. I don't know. And the estuary was literally Puget Sound with forest levels routinely 25, which is not like this estuary, but this looks a lot like this estuary, this reflectance does, right? Yeah, a lot of CDOM. And the coastal also included Gulf of Maine. So I included the entirety of the Gulf of Maine in that coastal set. So, all right, why don't we head out and then we'll pick this up after lunch. Second. Everything you need to do. Here's my clicker. Anyone see what I did with the clicker? If anyone sees the clicker, let me know. I hid it from myself. Okay, so here we were back marveling at the fact that the 6-component model explains such incredible range of spectral variability and reflectance. And so after figuring that part out, one of the things that I noticed in this was that, of course, the model doesn't have fluorescence in it, but the measurements do, and so you can exploit that, right? And at the time, and still 100 years later, there's still very little work that has been done to exploit the natural fluorescence signal, okay? And what's interesting about the fluorescent signal is, like, as Emmanuel mentioned, it is the only signal arising from the ocean that is only from phytoplankton. So that becomes really important. So what you see here is what the shape of the reflectance would be in the absence. And what were you surprised about?
It was, I was surprised that the model which didn't include fluorescence was showing some fluorescence.
It has a peak. So the question is, what the heck? What is this feature? This model only has absorption and backscattering, and it doesn't have any spectral features in the backscattering. What are we looking at?
The lines from the reviews back, a lack of absorption.
So it's actually the presence of absorption. That is the loss of reflected light due to the red peak absorption by phytoplankton. And no one had really noticed this before. And so when they were doing absorption line heights, they would just draw a line across their measured spectra and then estimate the line height. But look at how much you're overestimating the line height, because there's actual feature here that is backscattering of unabsorbed red light at the tail end of the absorption peak. And so one of the things that this model allows you to do is to reconstruct the actual fluorescence spectrum, accurately modeling out the differential absorption and backscattering. So you can see that this basically would come down and connect here, right? And so you would be vastly different estimates of your line height if you just drew a straight line across your measured spectrum. And so what I did is I actually did that for all of them, and I plotted up the different fluorescence spectra, and you can see that they're different shapes depending kind of upon the environment. Part of that is there's reabsorption of fluorescent light by phytoplankton, reabsorption of fluorescent light by other particulate matter in the ocean. And so by being able to actually get the fluorescence spectrum, it can tell you a lot about other processes of inversion. I didn't do that, but one could, right? This is your interest. It's a really great way of getting an unbiased fluorescence spectrum. Okay, so then the next part is to validate the model. So my advisor was very anti-chlorophyll and was like, "We don't need chlorophyll to validate anything. We should do everything with IOPs." And so nobody measured chlorophyll on these cruises. And so I estimated chlorophyll by using the absorption line height and measured from a filter pad. And that is what is on here. And then I did the estimation of the chlorophyll from the modeled absorption line height for these cruises, and then just compared the results, validated these results. And so what you see is over a large dynamic range, the model actually does a really good job in estimating the chlorophyll concentration, or actually the absorption line. In terms of phytoplankton absorption in the blue, there's a lot more going on in the blue, and so one wouldn't expect that the model would do such a good job in blue absorption, but in fact, over 3 orders of dynamic range, it also does a pretty good job. And these were measured using the filter technique, and this was estimated from the model. And then finally, we didn't have backscattering sensors, so the estimated backscattering, I related it to something that I did have, which was a Coulter counter. And so I used a Coulter counter to estimate the absorption of the geometric cross-section of the particles, all the particles in the sample, thinking that scattering should be most related to the cross-section, which is what we learned, right? And so for those samples where I had that, you can see that it was a really, really tight fit. So in terms of validating the backscattering, it was, based on mean theory, it was pretty good. So, all right. So then this gets into the model of residuals. And again, you have this first estimate, which is your basis vector times whatever coefficient you estimated. But the second estimate is actually, as I said, using the residual between the measured and the model and seeing what information that can provide, because something is causing the measured reflectance to be different from the model. And so if you just take the difference between modeled and measured and convert it back to absorption and add it to this model first guess here, you end up with, in that region, which would be, say, for this example, let's say, we've got the model is lower than the measured. So that says that the model has too much absorption in it. So it says that there's too much blue absorption compared to what's in the water. And so you just add it back in. And so here's the example here. And this is the shape that went in. The heavy line is the shape that comes out by doing this, adding the residual in, and then the thin line is what I measured with a spectrophotometer. And so what you see is there's a big difference here, and part of it is a signal to noise problem, but it's really, really different than the basis vector that went into the model. So what that said to me was that the features that are here that are not, where there's a residual, that contains information that's useful. And if you look at it spectrally, it can tell you something about pigments that were in your model or missing from your model. And so you can get something closer to spectral variability by absorption. Okay. Or, more importantly, moving forward, that you can add more phytoplankton components to the model to get a better job at reconstructing those various parts of the spectrum. Okay, this is just a sensitivity analysis. One of the things that's important about sensitivity analysis is it points out the weaknesses of the model. And what's true for all of these models is that they all do a really good job estimating phytoplankton absorption, because phytoplankton absorption has lots of peaks to fit. CDUM absorption looks like what? NAP looks like what? Particle backscattering looks like what? Great. And there's, one of them is in the numerator, one of them is in the denominator, and so you can imagine there's a lot of transference and variance between those components, and so those are not as well retrieved. So retrieving, something that is exponential in nature is tough to do. Okay. So, so this approach gives you a really good estimate of the component IOPs. The assumption is what the eigenvectors that you put in are, robust for your region, but variations provide you with so much more information that you can get out of them. And so, like, one of the things that a lot of people try to do with these models is to change your phytoplankton. But I think it would be really important to change your backscattering, because you have to get validation for spectral backscattering, and that would be a really fun thing to do. Is to think about ways of modifying that eigenvector. So I want you to, so I have a bunch of information about different parameterizations of the model and sort of being able to estimate things like beam attenuation, being able to estimate backscattering ratio, being able to estimate contributions by different phytoplankton species. There's a variety of different publications since the 90s where people have used this approach. And so there's a PDF that's like lecture 23B, like other models. So you can go through that. And then there's also one 23C, which is going through the details of QSM or GSM, QAA, and Hogan Lion, sort of looking at the specifics about how each of those algorithms work. But, so anyway, yeah, phytoplankton, inversion for pigments, reformulating to get beam attenuation, and the linear matrix inversion, which is really a cool way to linearize the equation. And it allows you to get uncertainty on each one of the eigenvalues, which none of the other models can get. So that's a really cool example. All right, powerful tool. Devil is in the details as usual. There's a bunch of different solution methods. And, things for you to consider, just making sure you have independent data for testing and adding uncertainties into your estimates. So what we're going to do in lab today, I'm giving you an Excel file. We're going to do inversions by hand to see who can get the best inversion by eye. There's some reasons why I do that. Having you do it by hand first, it makes you so happy to have MATLAB code. Then I'll give you the code that I've written, which gives you different models, where you have one component of phytoplankton, two components of NAP and CDOM, two components of basket, every combination that you can put in, and a bunch of different eigenvectors, and you can just run them all. I'm giving you data sets, and we're also giving you a simulated data set from HERT, from Hydrolite, that actually has validation data because you know what generated the reflecting spectrum, so you should be able to retrieve that. You can put your own data in there. And I have tried to document the code such that it will be really easy for you to modify it for whatever you want to do. I have left all the details in there, all the cost functions in there, all the nitty gritty, so that you can take it home and make it yours. And you can rewrite it to put any other model in there that you want. I mean, it's very flexible, but it's a starting point, because sometimes not knowing how to do an inversion model or a nonlinear regression seems a little daunting, but if it isn't, if it is for you, then this is the code for you. If you already can write your own and do it, but hopefully it's will be helpful. Okay. Questions?
So the eigenvalues are the coefficients in your model, those are not spectrum, right?
No, they're just the concentration part. They're just telling you how much of the spectrum where the eigenvector.
So it's basically the same value for
Well, what varies with wavelength is the eigenvector, right? That's the spectrum, say, for phytoplankton absorption. So that is constant. And then you're estimating how much the spectrum best reconstructs the measured reflectance. So it's a scalar, which you're estimating, times the vector, which you're providing. Okay. All right. I was going to say we do the lab in the other room, but it feels hot in here, and I'm guessing that it's really hot in there. So do you want to take a break? Do you want to just get started? Get started. Okay. So download the lab. I'm stopping. Never find a mouse.